buoyancy, or buoyant force. As an object is submerged in a fluid, whether it be a liquid or a gas, there is an upward push on the thing, on that object. We want to try to explain why that is true. So, at the end of this lesson, you should be able to explain how liquid pressure creates a buoyant force. And then we would like to be able to explain how that buoyant force is related to the weight of the fluid that is displaced. So when that object is submerged in a fluid, it's pushing fluid to the side, and we call that displaced fluid. And then we'd like to be able to explain why an object will sink or float based on the buoyant force as it compares to the weight of the object itself. First, a reminder that pressure in a liquid is density times gravity times height. And density and gravity are constants. And if we were to graph the pressure as a function of the depth or the height, this term and this term would multiply together to give us a constant, which would be the slope of that line. So if we have depth on the x-axis and pressure on the y-axis, because those two things are constant, it is a straight line, which means if you go down 1 meter deep, you'll get an increase in pressure. If you go down 1 more meter, you'll get the same change in pressure or increase. So if we just did that with water, but rotated up like this, and the pressure increases linearly. And that's important to remember. But if we drilled a hole and water had a little bit of pressure and spewed out a little bit here, if you went twice as deep or 3 times as deep or 4 times as deep, the pressure would increase by the same amount at every increase in depth. All right, so if we had that pushing against this wall now, and we have an object submerged in there, the water is going to be pushing up on that thing with what's called a buoyant force. But remember, liquid pressure, it comes from collisions of molecules banging into the surface, and those molecules are going in every direction. So it's not just pressure against the outside wall here, it's pressure against this wall and pressure against this wall. And this top edge of that wall is at the same depth as that whole surface there. So there is pressure all the way around. Again, the pressure here was the same as the pressure there, but just pushing against the surface, or normal too. The pressure at this depth would be the same as the pressure at this depth, but just pushing normal to that surface versus normal to that surface. But if you look at it, all these little forces pressing down on little areas here are trying to push that thing down. And these pressures, or all these little forces pushing in their little areas, are pushing up. And so we got pressure pushing down, we got pressure pushing up, and the difference is going to be what's called, or is what is creating the buoyant force. Now, if that object were submerged deeper, what do you think would happen to the buoyant force? Do you think it would increase, decrease, or stay the same? Now that you've guessed, the answer is it will stay the same. And that's because pressure increases linearly. That as that thing is deeper, there's more pressure all the way around. And the pressure pushing to the left is balanced by the pressure pushing to the right. But the pressure against the top is always going to be less than the pressure against the bottom. Or you could say the pressure against the bottom is always going to be greater than the pressure against the top. The reason is the bottom is always going to be deeper. That's just the way the depth thing works. So here we had all these little forces pushing on their respective areas. That was here. And we had all those forces pushing on their respective areas. But the difference, there created a net force in that direction, which is the same thing. So you got force pushing up. That's the pressure against the bottom of the object. force pushing down, that's the force against the top. The difference of those is the buoyant force. Down here, we had more force up and more force down, but the force up was still larger than the force down, and the difference is what created the buoyant force. Now we take an object like this, and let's see if you can guess which of these two objects has a larger buoyant force. Now that you've guessed, you might guess that this one had a bigger buoyant force because there was a bigger difference in pressure. But we'll take that linear increase in pressure with depth. And so the top is at this depth and the bottom is at this depth. So they have all these little forces pushing on their little areas and these here. And the top here was at that depth and the bottom here was at that depth. These arrows are just as long as those arrows. But what we see is if we take all the forces pushing up, subtract them from all the forces pushing down, the difference is the buoyant force. And we're going to do the same thing here. We're going to take all those forces pushing up, subtract them from all the forces pushing down, and we get the same buoyant force. And that might be a little surprising. But pressure is force divided by area, or force is pressure times area. Just rearranging that. The buoyant force comes because there is a difference in pressure and an area that pressure was different. So this area is pretty small. This area was pretty big. So this had a big difference in pressure because there was a lot of difference in depth, but it was on a small area. This had a smaller difference in pressure. There wasn't as big of a difference in depth, but it was over a bigger area. And the balance of those two variables work out to be the same buoyant force. Now again, remember that the pressure comes from molecules colliding into the surfaces. And if a molecule hits at an angle and collides into that surface, it's only the component that's normal to the surface that results in a force against that surface. But all along the bottom of the ball here, it's those forces are bigger because it's deeper. All along the top, those forces are smaller because it's not as deep, but they result in a net force in the upward direction called the buoyant force. And there's a cool demonstration you can do. These are ping pong balls in acrylic tube that is filled with water. And you can put that on a drill and spin that drill around really fast. And right now, this ping pong ball has more pressure against the bottom than the top because gravity's pulling that water down and more pressure on the bottom of the ball. But if you spin that thing around like this, the pressure, and you have to think back to centripetal acceleration. If the water is accelerating toward the center, it's actually going to create more pressure on the outside of that ball than the inside, and the ball will be buoyed toward the center. And because the tube is at an angle, it can only move toward the center by going along this diagonal there. There's a lab that we can do that will actually be able to calculate what the buoyant force is. And in the lab, the objective would be to determine the relationship between how hard the water pushes up, that's the buoyant force, and how that's related to the weight of the water that was displaced by the object that's in the water. So one has this little boat that's going to float in a beaker of water and then a pan to collect the water. The other one would use an electronic balance that, electronic balance is you could place an object up top here and it would weigh it. But this balance has a hook that you could tie a string underneath this and then weigh something while it's hanging. So here's the first thing. We got our water here. It's filled to the rim, and you mark where that is. Then you place this boat in here, and all sorts of water is going to just get displaced because the water can't take up where the boat is. And all that water spilled over into this thing here. Remember the objective. The objective was to find a relationship between the buoyant force and the weight of the water displaced. Our objective was to find a relationship between those two variables. Well, one clever thing here is that if this boat is floating, if it's not accelerating, the net force on that boat is zero. So if gravity is pulling down with some force, the water must be pushing up with an equal amount of force. So all I have to do to measure the buoyant force is to figure out what that cup weighs. Because again, it's not accelerating, so the net force is zero. The downward force due to gravity must equal the upward force due to buoyancy. And that's if it's floating. It's not going to be the case if it's submerged or sunk. But what we have to do is weigh all this water that got displaced and then compare it to the buoyant force. The other part is we had a mass here, and it would weigh about 450 grams hanging there. If we submerged it in water and then measured it, it would weigh less because the water was pushing up on it. And if we subtracted those two numbers, we could find how hard the water was pushing up. So 44.4 grams would be the buoyant force. Now, I always cringe when I talk about grams and force. Really, grams is a unit of mass. We'd have to convert it to kilograms and then multiply by 9.8 to get newtons of force. But we'll let it go this time. So that's how we measure the buoyant force. Now we wanted to measure the weight of the water displaced. So we watch very carefully where the water is here. We set this mass in here, and when it touches the water, it's going to displace water up to a new volume. And the difference in those would be the volume of the water displaced. Now, if we were to weigh that volume, if you remember the density of water, that 1 milliliter of water has a mass of 1 gram, 44.4 milliliters of water would have a mass of 44.4 grams. And if you remember from the previous slide, we measured the buoyant force, it was 44.4 grams, and then the weight of the water displaced was the same thing. So it looks like the buoyant force, and here, don't miss this, this is it. The buoyant force equals the weight of the fluid displaced. Okay, let's see if we can put that to the test here. Let's say we have an object here and it weighs about 20 newtons out of water. When we set that in water, it's going to spill water off to the side. It's going to displace water. Now the scale only reads 13 newtons. So what was the buoyant force? Well, the water must have been pushing up with 7 newtons because it weighed 7 newtons less. But what do you think the weight of the fluid displaced is going to be? And that's just the mind-boggling thing, is that the water that is in here, whatever that water weighs, is going to be the same force as the water that is in here pushing up on our submerged thing. So again, let me just say that so carefully. The buoyant force equals the weight of the water displaced. Okay, and this is also known as Archimedes Principle. And Archimedes discovered this a long, long time ago. And this story goes that Hero was the king of the area, and he had a crown that he had given a goldsmith a certain weight of gold, and told the goldsmith to make him a crown and use every single grain of gold in that. And then when the goldsmith brought the crown back to Hero, it was beautiful, beautiful crown, but Hero noticed that the color was maybe just a little different. It didn't look like it was pure gold. And then the king started to wonder what would happen if the goldsmith had put maybe some silver mixed with the gold and kept some of the gold for himself. So he asked Archimedes if he could do a test to see if it was pure gold or not. Now, this was a long time ago, so it was a difficult thing. What Archimedes came up with was, knowing that silver is less dense than gold, if the crown had silver mixed in with it, it would have a larger volume than pure gold, the same weight of pure gold. So if this is 10 pounds of crown and this is 10 pounds of pure gold, if you dipped it in here and spilled water over to the side, or dipped this into here and spilled water over the side, if this was pure gold and the crown was pure gold, the volume would be the same if they had the same weight. Now, that's how the story typically goes, but that's probably not how Archimedes did this, because these are clay pots, and it would be a very small difference in volume that Archimedes may not have been able to measure. A way that is maybe more likely that he would have done it is to have the 10-pound crown here and 10 pounds of pure gold on a balance. So they would be balanced out of air because they had the same weight. But if this had a larger volume, if it was mixed with silver that was less dense, to make up the same weight, you would need a bigger volume. Then this would have displaced more water than what that did, so the buoyant force would have been bigger on this object than over here. So out of water, this weighs 10 pounds, and this weighs 10 pounds. But if this had a bigger volume, I'm just making up numbers here, but the buoyant force may have displaced 3 pounds of water, and this would have only displaced maybe 2 pounds of water because that was less dense, or sorry, it was more dense and took on a smaller volume. So Archimedes' principle states the buoyant force equals the weight of the fluid displaced. I say that over and over and over, but it's so important to understand that. So if I wanted to calculate the buoyant force on this submerged ball, I'm not going to measure, I'm going to calculate it. So to calculate the buoyant force, I would have to calculate the weight of the fluid displaced. Well, the volume of this sphere is 4/3 pi r cubed. I'm giving the radius. So when you plug in the radius there, you would get that this has 92 cubic centimeters of volume. That's the ball. Because it's submerged, it's going to displace that amount of water. Okay? And knowing the density of water and the volume of that water, you can find the mass of that water. So the density of water is 1 gram per cubic centimeter. The volume was 92 cubic centimeters. So the water displaced should be about 92 grams. And then convert grams to kilograms, multiply by 9.8 to get it into newtons. The buoyant force would be about 0.9 newtons. Now, I'm hoping at some point in your life you've been in a swimming pool with a 5-gallon bucket and tried to push that bucket into the water upside down. It's hard to do that. And the question is, how hard is it? Okay, not just is it hard, but how hard? Well, if this is a 5-gallon bucket and you push it until water starts to spill in, it's displacing 5 gallons of water. So it would be just as hard to push that thing down as it would be to lift 5 gallons of water. And knowing that this is 5 gallons and the density of water is 1 gram per cubic centimeter, but in these units, it's 8.3 pounds per gallon. We had 5 gallons. It's going to be about 42 pounds. So you could lift with 42 pounds, or when you push this in, you're displacing 42 pounds of water. That's what the buoyant force would be. So you have to push with at least that to get it to go down. And then maybe you've seen the Pirates of the Caribbean, where they put the boat upside down and they try to get away. And that's totally possible in terms of being able to breathe underwater and encapsulate a bubble of air. But let's mark along the edge here and let's try to estimate the buoyant force. Now, we have a 55-gallon drum here, and I'm guessing maybe a little less than 4 of those could pour into that volume there. Maybe about 200 gallons of water was displaced by that bubble. So knowing that 8.3 pounds for each gallon and 200 gallons were displaced, that's about 1,700 pounds of water was displaced by that air bubble, which means the buoyant force is going to be 1,700 pounds. So when they're underwater like this, no problem, that so could happen, but the force pushing them up would be about 1,700 pounds. So for them to be pushed against the ground, the boat itself would have to be more than 1,700 pounds. And so no problem there, but if that's where I have the problem, the boat would have to be about 1,700 pounds or more, which I don't think even Johnny Depp or Orlando Bloom could do that. All right. This seems like a simple question. I show two examples and I ask which one has a larger buoyant force. And you can't go with your gut instinct. Okay, you have to think very carefully about it. So if the buoyant force equals the weight of the fluid displaced, and I ask which object has a larger buoyant force, well, it's the same question as asking which object displaces a greater weight of fluid, because the buoyant force equals the weight of the fluid displaced. I would try not to answer this question, but rather try to answer this question. This one seems to indicate more about what's going on. So let's say we have water, we have a billiard ball, we have a racquetball, and they're the same size. And let me ask, which of these two objects experiences a larger buoyant force? Now that you've had a chance to respond, the answer is the billiard ball. And you might be surprised at that. But if you answer this question, you might be tempted to say, well, that one was pushed to the top. This one didn't have as big of a push to the top, so it fell down. Well, that's only part of the story. If we ask which one displaces a greater weight of fluid, that is an easier question to answer, because this one displaces everything from there under here. So that little sliver there is what's being displaced. This one is displacing all of that material. And so this one displaces much more water than that. And that water is going to weigh more. So it has a larger buoyant force. Let's try this one. Let's say that we have a metal sphere, but it's hollow inside, and it weighs about 2 newtons and pretty large. And then we have a solid metal sphere, so it's much more dense, and it's going to be a lot smaller in volume, but it weighs the same. And then we put them both in water. This one floats, this one sinks. And the same question, which one of these two objects has a greater buoyant force? And again, you might be tempted to say this one did. And you are correct if you did. The reason being is this one displaces that much water. This one only displaced that much water. That's a lot larger volume of water. And that volume of water is going to weigh more. And remember, the buoyant force is equal to the weight of the fluid displaced. All right. And if these two objects are submerged, which one has a larger buoyant force? Well, it's going to be the same right now. So because they have the same volume, they're displacing the same volume of water, and that volume of water for each of them would weigh the same. Okay, so they have the same buoyant force, but that's not the only force acting on these two objects. Isn't gravity pulling down on each of these? Now, this is a billiard ball. It's going to be a lot heavier than a hollow racquetball. So the upward force on these was the same, but the downward force was greater. If we look at the net force, this had a net force in the down direction. This had a net force in the up direction. So if we were holding those there, this is the situation that it would be. But if we let go of them, it would accelerate down and that would accelerate up. This would float, this would sink. All right, so if this is floating, the buoyant force, that upward push, has to equal the weight of the object. If it's not accelerating, those two forces are equal and opposite, so the net force is 0. So if you weigh the racquetball, that's the weight of it here. And then this little sliver is what's being displaced. So that water over here would be equal to the weight of that water would be the buoyant force, and they would stay balanced. If you submerge this under the water, now you're displacing a lot more volume, and that would weigh more. Since the weight of the water displaced was greater than the weight of the object, the buoyant force would be greater than the weight of the object, and it would have a net force up. Put a billiard ball in here that's already submerged. You have all that's is the weight of the billiard ball. This is the weight of the water displaced, and that will sink like this, which means it weighs more than the weight of the water displaced. Okay, so that's just recapping that. Let's see how we do here. If I had 1 kilogram of lead, or I had 1 kilogram of aluminum, and they're both submerged in a fluid, which one's going to have a larger buoyant force? Now that you've had a chance to answer, it is the aluminum is going to have a bigger buoyant force. And that's because we have to understand that aluminum is a lot less dense than lead is. Lead, 1 kilogram of lead is going to be this big. 1 kilogram of aluminum is going to be a lot bigger because it's not nearly as dense. So the buoyant force would be, this is displacing a lot more fluid, and it's going to have a bigger buoyant force. Okay. All right, and that's just saying the same thing again. The weight of the fluid displaced was greater, so the buoyant force was greater. Now, if I had 1 liter of lead and 1 liter of aluminum, which would have a larger buoyant force, well, liter is a unit of volume, not mass. So the size of this and the size of that are the same. And so each is going to displace the same amount of fluid. The buoyant force would be the same. All right, buoyant force equals the weight of the fluid displaced. When something's on the surface, floating, the upward force from the water has to equal the downward force due to the weight of the object. The net force would be 0. Okay. And since the buoyant force is equal to the weight of the fluid displaced, this term here has to equal this term here. So the weight of the fluid displaced must equal the weight of the object itself. Now, this is a very important distinction to make. Either something is floating or something is submerged. When something is floating, 2 things are going to be equal. But we have to think what 2 things are going to be equal. When something's floating, the weight of the object is going to equal the weight of that little bit of water that's displaced, because gravity pulling down and then the weight of the water displaced is the buoyant force. They are equal. Otherwise, that thing would be accelerating. So when floating, the object equals the weight of the fluid displaced. When submerged, 2 things are equal. And what is equal? Well, that's the size of the ball, and that's the size of the water displaced. So they have equal volumes. And that's relatively obvious, but very important distinction. When something is submerged, the volume of the object and the volume of the water displaced are equal. When something is floating, it's the weight of the object and the weight of the fluid displaced that are equal. I'm going to stop there, and we'll do some more examples in the next video.